So, good afternoon, ladies and gentlemen. I'm Yannis Anastasopoulos, I'm chair of TC104, and I would like to welcome you to the interactive webinar series of the Technical Committee of Physical Modeling in Geotechnics. The webinar series is a new thing. We have just introduced it, and it aims to combine the knowledge of experienced researchers with a passion and drive of early-stage researchers, but also the extremely important contribution of technicians. So we try to have a combination of speakers, as you see. I will introduce the speakers right after. A key goal of these webinars is to share our experiences, try to learn from the challenges that we are facing when performing physical modeling. And for these reasons, to try to achieve these goals, we will try to make the webinars to be as interactive as possible, promoting active involvement and participation of everybody who is present. Recognizing that we can learn more from failures, it would be nice, this is not mandatory of course, but it's nice to share also problems that we have faced and how we solve them. And this applies to the speakers, but also the participants, because everybody can contribute with their experiences. The webinars are fully open, and I see that we have a lot of attendees who have just connected, and maybe more will connect next. But also they are recorded, so that we will post them later in the TC104 website, so that other members who could not make it at the moment can see them later. So today's webinar, which was supposed to be the second, but because we had to postpone the first one, this is the first one actually in the end, is on advancements in the characterization and preparation of HPMC viscous fluids for centrifuge testing. And as you can see, we have 4 speakers: Tristan Quinten, who is a PhD student at TU Delft; Miguel Cabrera, who is an assistant professor at the same university; Roland Klassen, who is a lab technician and area supervisor, also at TU Delft; and Amin Askarinejad, who is associate professor at Delft University of Technology, and also the director of research and development at the dam safety section of the Swiss Federal Office of Energy. So I would like to welcome you all. I would like to thank our speakers for their contribution. And before giving the word so that the presentation can start to the speakers, a few things about the process. Please mute everybody, mute yourself, so that we don't have, except the speakers of course, so that we don't have any strange noises. The presentation will be split in blocks. We start with one block, then we have a pause for questions in an attempt to make it as interactive as possible. So then whoever wants to ask a question, raise your virtual hand, activate your camera, your microphone to ask your question, and then we proceed with a remaining block. So we will not wait for the questions at the end, because then many times we forget what we wanted to ask. We try to do it as interactive as possible, but without splitting, let's say, too much. So I stop sharing my screen, and I give the word to, I think Amin is starting. So Amin, the floor is yours.
Thank you very much, Yannis. I'm trying to share my screen. Please let me know if it is visible.
Yes, it's fine. We can see it.
Perfect. Thank you very much. Hello from my side. Good afternoon, good morning to everybody. And I'm going to present just the introduction, and my colleagues Tristan Quinten and Miguel Cabrera are going to take over the rest of the presentation. And as Yannis mentioned, the topic is about the experience that we have developed over a couple of years at TU Delft in developing a new methodology for preparation and characterization of HPMC viscous fluid for centrifuge modeling. So to just give a very short introduction to centrifuge modeling, I guess everybody knows why we use centrifuges, but I thought I'd give a very short introduction to that. Of course, the main goal of centrifuge modeling is to study the behavior of geotechnical structures using small scale models, which facilitate a relatively fast and reliable testing environment. So we know that the shear strength is a very important parameter for us as geotechnical engineers, and for many porous materials, it is dependent on effective stresses. Therefore, when we geometrically scale down our geotechnical structure, we need to enhance the gravity to make sure that the stresses are the same in the model and in the prototype. Here I have shown a picture of a Dutch dike, and let's assume we would like to check the seismic performance of such a structure. When we take an element at a certain depth, here P stands for prototype. The total vertical stress at a certain point inside this dike below the surface is the unit weight of the material multiplied by the depth. So the height of the column, the soil column above this element. And if we decompose this gamma, this unit weight, we would have density and gravity, or the gravitational acceleration. Let's say this dike is 5 meters high, and we make a 100 times smaller model. So the dike in the model, which we are going to put in the centrifuge, would be only 5 centimeters. If we look at the same element or the same corresponding element in our model, the depth from the surface to this location of this soil element would be n times smaller. In this case, 100 times smaller. And the effective stress at this location would be again gamma of the material of the model that we have used, multiplied by the depth of this element. Therefore, we can again decompose this gamma into density and the gravitational accelerations. And as we are increasing the gravitational acceleration in the centrifuge by the scaling factor that we have used for geometry, we would see that the stresses in the model and in the prototype would be the same. Or this is, of course, upon the condition that we use materials that have the same densities. And I have to say here that in this example, I have ignored the pore pressures, and later on I'm going to come back to this. So, of course, we have a lot of scaling, and one of the very challenging points about scaling in centrifuge is the scaling law for time in our modeling. I would like to focus my attention on two processes. The first one is the scaling factor for time when we are simulating dynamic processes. We know that the acceleration in the prototype is n times less than the acceleration in the model. So in the model, we are applying n times higher accelerations. And when we look at we do a dimensional analysis on acceleration. Acceleration has a dimension of length divided by time to the power of 2. And we know that the length in the model is n times smaller than in the prototype. Therefore, if we apply this basic rule, we would see that the dynamic time in the model would be n times smaller than the dynamic time in the prototype. What does this mean? It means that when we, for example, have an offshore foundation subjected to some dynamic loading, and this dynamic loading is going to produce some pore pressures or induce some generation of excess pore water pressure, this pore pressure would be generated n times faster in our model comparing to the prototype. So let's have a look at the dissipation process or the flow process, so where we have a certain generated pore pressure or excess pore pressure, and then the time that it's going to dissipate. I'm not going to go into the details of the derivation of this equation, but we would see that the dissipation process is governed by a factor of 1 over N2. So it means that actually the generated excess pore water pressures due to dynamic loading would dissipate faster in our centrifuge comparing to the reality. And as discussed before, the soil shear strength is very much dependent on the effective stresses. Therefore, if we have a faster dissipation of pore water pressures, actually the soil might behave stronger in our model. And if you want to use these findings of the centrifuge testing for design, we are on the unconservative side. So, as a summary, in centrifuge modeling of dynamic processes such as offshore foundations or earthquake problems, the excess pore pressures are generated dynamically with a scaling factor of 1 over n, but the decay of the pore water pressure or excess pore pressure is governed by a factor of 1 over n2. So what are the solutions? The basic solution is that we should slow down the dissipation of the generated excess pore water pressure in our models. And how do we do that? Basically, there are two methods. The first one is to reduce the value of permeability by using finer material, or the other option is to use a pore fluid that has a kinematic viscosity higher than our prototype saturating fluid. In a lot of cases, that's water, and then we would have a lower hydraulic conductivity of the medium. The first option, which means that we are going to manipulate the grain size distribution of our material, might result in different constitutive behavior of the material, which would result perhaps in different behavior. Therefore, a lot of researchers basically have focused on the second option. And this is the topic of our presentation today. So a very important point is that the density of the pore fluid that is used as the scaled viscous pore fluid should be the same or very similar to that of water, so that we make sure that the hydrostatic pressures are comparable in the model and in the prototype. So a short review on the past experience in literature since 1990s. Over the past almost 30-40 years, there has been several attempts to develop such fluids, pore fluid for centrifuges. For example, there has been some attempts at ETH Zurich to have a mixture of glycerin and water. Or some attempts since 1990s with HPMC. That's the topic of our presentation today as well. Or at Deltares, there has been some tests with CMC and also some mixtures of water and kaolin. I think I'm going to give the floor to my colleague Tristan Quinton. So that's the end of my presentation part. Yannis, what do you suggest? Should we have the round of questions or should we continue?
Maybe yes. Are there any questions? Although this is very introductory, but
Exactly.
Are there any questions at this point by anyone? So maybe we proceed because
perfect. Then I stop sharing and I give the floor to Tristan Quinton.
Yes.
Thank you, Amin. I will also proceed with sharing my screen. I suppose this is visible for everybody right now, correct?
Yes, we can.
All right, excellent. So I will skip quickly through the slides of Amin. I can, and I will also make sure that I have a laser pointer. All right, so I will kick off with the part on the fluid preparation, which is, as Ioannis also explained, the second block of this presentation. In order to make these viscous fluids on the basis of HPMC, there is some literature available on the different kinds of preparation methods. So when we first started to think about how are we going to make these fluids, we decided that we would opt for an alternative that is called the hot-cold method. So the next 4 slides will basically illustrate this process in very basic terms. So the first step of this process, as is indicated over here on the left, is to heat a portion of the fluid to a temperature of 90 degrees Celsius. Now, if we use an outline that is available in literature, it generally says that you require between 25 and 33% of the fluid volume to be heated to 90 degrees Celsius. Now, when we started to do this, and also it's a little bit inside of the nature of this method, is that we realized because we are dealing with fluids of different temperatures, and also we need to cool it down later on, for which we could potentially use ice. Using volumes is a bit tricky. So it's actually better, as is also indicated at the bottom now, to express everything in terms of mass. So then the volumes can change, but in terms of mass, we know exactly what is our concentration. So the subsequent step is to add in the HPMC and then to thoroughly mix this under continued agitation in order to achieve a state of full dispersion of the powder. Now, the reason that this happens at a higher temperature is because the HPMC has properties which don't allow it to dissolve in high temperature water. So by leveraging this property, we can make sure that we have water surrounding our particles. And in this way, we can make sure that as soon as we start to cool down the temperature, we get the viscosity development occurring in the appropriate way. So that is then the next step. So we will add cold water or potentially ice. This is a little bit depending on the preference of the researchers. And then essentially what we will do is we would add the remaining mass of fluid as ice or water, and then make sure that the temperature of the entire solution drops below the hydration temperature. And in this case, we get the viscosity development of our fluid. So then the final step consists of 30 minutes of continued agitation. This is just to make sure that we are really certain that the viscosity has fully developed and we can proceed with processing the fluid for our desired purpose. Now, of course, and as also was introduced in the beginning of this webinar series, there were some challenges related to actually executing this according to the outline. So the first part is related to the heating of the material or of the water. And one of the things that we quickly realized is that the heating for the material that we were using was too slow. So you can see over here, we were using a small batch of water and we're using a small electric heating plate. And we were realizing that this was a very inefficient way of heating our material. So quite quickly, we came to the conclusion that if we were going to scale this, we should look at other alternatives. And eventually we realized that probably the best alternative was to use induction. Now, I suppose that many people are using induction in their kitchen as well. And this is a very nice and quick way in order to heat water, and especially heating large volumes of water. Now, obviously, as we are heating our fluid, we are dealing with evaporation. And because the process was initially very slow and we had an uncovered container, we were actually measuring quite a lot of evaporation. Now, especially if you're dealing with small volumes of fluid, we realized that the concentration that we desired and the concentration that we obtained at the end, they were two completely different things. So that caused some issues in our case, and we decided that, okay, this is something that we need to eliminate in order to make sure that we can reliably produce these fluids at our desired concentration. Now, the solution to this obviously is quite simple. I will just drag this to the other side. Well, actually, is this showing the... Okay. So we can cover up our container. We used 2 different methods. The first one was using parafilm, which is shown in figure B. And the second one was trying to use some sort of condensation device. In this case, it was very simple. It's a small stainless steel container with some cold water. and then it helps to go back from gas to a liquid. Now, in practice, it's actually easier to have something that doesn't involve adding water on top of your solution. So using a lid, as I also am indicating at the bottom of this slide right now, is the best solution. Now, in terms of the measurement of how much was evaporated, this actually also solved our issue there. So if you completely eliminate the evaporation, we also don't have to worry about measuring how much we are losing during the heating process and the subsequent cooling. So this essentially solved two issues at the same time for us. Now, this next challenge that we faced was the dispersion of this powder. So what we quickly realized is that the method that we were using, especially for these small batches, was not capable of dispersing this fluid or the HPMC adequately. And the result of this is shown here over here in figure A. What we were finding is that as soon as we added the cold water in order to get the finalized fluid, we would end up with something that's completely cloudy. So we could also see some particles, like colligated particles sticking together in some sort of hydrophobic form. And also what we realized there is that the viscosity that we designed for was not obtained. We were way off, like way lower. So in order to solve this, we need to make sure that we use the right blade in order to disperse this fluid properly inside of the hot water, which generally means that you need a dispersion mixing blade. And also you should make sure that the stirrer that you're using is capable of agitating the entire volume of water. So when you are picking your overhead stirrer, this is something that you should account for. But then even as we obtained a nice clear solution at the end, we realized that there were still some suspended impurities inside of our solution. And now our guess here was that probably this was due to the fact that we were using an industrial kind of HPMC that could have some contaminations. And those contaminations, they don't dissolve in the water. So what you end up with is sort of a suspension of these really fine particles. Now, this could be problematic if you're using a very fine granular material as your model soil, that you could get clogging of the pores. So in order to eliminate this, we decided that we would incorporate a filtering process and then filter out all of these impurities, after which we realized that we would not change the viscosity, we would just get rid of these small floating particles. So that then brings us to the finalized setup here. Over here on the left-hand side, I have a schematic of the system, and over here on the right-hand side, you can see the setup as we have over here in the lab. So at the bottom here, I've sort of included the different requirements that we formulated based on our experiments. And then if we go one by one, we can see that we have now an induction hub, which is also highlighted in blue over here in the middle picture. We are sealing our vessel or our reactor, which is now stainless steel. It's not glass anymore. That has to do with the induction. And in the case of our physical setup, we are using an acrylic lid so that we can also see what's going on inside. And as is also shown in the schematic here, we have a small opening to add water or potentially add the HPMC powder. Subsequently, we are using a dispersion mixing blade. So that looks like this. Also, the size of this blade, it needs to be correct in relation to the size of your container. So we spent some time finding the right size for the reactor that we are using. And it needs to be connected to the right type of overhead stirrer. So in the end, we decided to go for this type, which is perfectly capable of agitating approximately 35 to 40 liters of fluid, which is more or less the amount that we are making in one go currently. And then at the end, as previously explained, we wanted to filter our solution. So here you can see a filter housing, which has a candlestick of a filter inside. The porosity of our filter is 5 micron. And then you can see that there's 2 pressure gauges in order to measure the head difference over our filter. And the nice thing about this is that it gives us an impression of the condition of our filter. And then we can define a criterion on which we would basically decide to replace the filter in order to keep the properties of our fluids the same. So the final slide is basically showing the whole system. There's 2 things that I have not touched upon, which is a pump that essentially pumps the fluid from the reactor into the filter, because otherwise it would take a very, very long time if you would just use the head difference. And the other point that I did not explain in that much detail is the reactor with a little bit of the temperature gauge on the outside, but we also have a digital thermometer on the inside in order to measure the temperature of the solution as we are mixing it. So this brings me to the end of my first block. Johannes, I will give the floor back to you to see if there's maybe any questions from the audience.
Yes, thank you very much. So let's see, let's open for questions. Are there any questions until now? Okay, I see somebody's raising their hand. So, Sumin.
Hi, can you
Hello.
hear me?
Yes, can hear you.
Yes, yes.
Yeah, I'm Sumin from University of California, Davis, and thank you for the presentation. So I'm also using HPMC solution. So I have a question about the preparation of the solution. So you mentioned like in like second stage, like how do I know when like everything is dispersed and like well mixed so that I can like move on to the next stage of like adding cold water? So
Okay.
do you have any criteria like mixing for like 30 minutes is enough or like something like that?
Yeah, so this is a very good question. Yeah, so this was basically, for us, it was sort of based on a trial and error. I think right now what we are doing is we are adding in the HPMC and then we're really agitating, I think at the maximum RPM that can be sustained by our mixer in order to make sure that we really are properly dispersing this fluid. And based on the experience that we have gained from this, after approximately 10 to 15 minutes of agitation, provided, of course, that all of the hardware that you're using is up to the task, it will eventually yield a nice and uniform solution after you've added the cold water and then essentially waited for it to cool down until room temperature.
Thank you.
I hope that answers your question. It's not really a hard requirement, but yeah, 10 to 15 minutes, I would say, is more than sufficient.
Thank you.
I wanted to ask you, take advantage of, being the chair of this. I wanted to ask a question. Have you looked at the procedures that were developed during the LEAP project? And how different is it to what you do compared to what the LEAP recommendations were?
So I'm not completely familiar, I'm afraid, with the project that you just mentioned. But if I sort of draw from the experience that I got from doing the literature review based on this, is that in many of the papers that I have read, there is not that much detail on exactly how these solutions are prepared, other than a general outline, as I have also presented in the first couple of slides of this section. So that was also one of the gaps that we would potentially try to try to fix, to be more specific about the hardware that we are using and the process that is related to making these fluids.
And did you notice, is there any change of the viscosity with time? Is it sensitive to the time that passes?
So we looked at literature as well, and then I think there's a couple of researchers that retested the fluid at approximately 3 months after preparing it. I personally have experience in testing this fluid 9 to 12 months after preparation. And when I retested it with the rheometer, the viscosity was still exactly the same.
Okay.
So I suppose that if the storage conditions are appropriate, this will keep good for quite a long period of time.
Provided that you don't have any evaporation, I suppose.
Yeah, so exactly. So we're closing it off in containers with a lid, and then they're stored cold in a storage room and also in the dark. So there's no room for algae, for example, to grow inside of our solution.
Any other questions from the audience? Maybe ask one more general question, because I suppose many people here are experts, but maybe some are not experts and would like to learn. And this is for you or also for Amin. So could you explain in a little more detail, why do we need a high viscosity fluid? What is the reason, the physics behind this? So maybe this is probably for the part of Amin.
Exactly. So, I mean, would you be able to answer this question?
I will try. So, so your question, Yanis, is the fundamental requirement for use of higher viscosity.
Yes.
For the
Why do
fluid.
I mean I know the answer. I just want
Yes.
to prompt your
Yeah.
response for someone who is not so familiar with these topics.
Exactly. Well, it is basically hidden in the scaling factors. Maybe Tristan, if you scroll back up to slide 5, or maybe I can share my screen.
No, I think Tristan has
Yeah,
it.
I think that's easiest. Yes. So basically, especially during dynamic processes, we have two events that can affect the behavior of the soil considerably. One of them is that there is an increase in pore water pressure, or so-called generation of excess pore water pressures. And as we see in the upper equation, that is dominated by the dynamic loading that is imposed to the structure. So by the, let's say, frequency content of an earthquake, or the in the case of pile driving, by the impact energy, and also the duration between successive impacts. And if we look at the upper equation, we see that the time of generation of pore water pressure is governed by a scaling factor of 1/n. And the second process in terms of this generation and dissipation of pore pressure, excess pore pressure, is the dissipation of that. And we see the scaling factor for that in the lower equation, which is 1/n2. And we see that actually the 1/n2 is n times smaller than the generation. So when we compare our model with the reality, we see that it's going to dissipate much faster than what it happens in reality. So if an earthquake, let's say, causes development of excess pore water pressure, and then it remains for a couple of seconds after the event, in the centrifuge model, if we use water, these couple of seconds would be a couple of milliseconds, or tenths of a second, and then immediately it would decay. In order to avoid this, we need to decrease the permeability or hydraulic conductivity. And one of the most used ways is to use the viscous fluid.
So our problem is permeability, and
In fact, yes.
And the fact that it's not easy to scale down the particle size, right?
Yeah, it's going to exactly. Maybe Tristan, if you go to the next slide. In fact, there are two options that we have. One of them is to decrease the particle size. So let's say if you use the Hazen equation, the permeability is related to the d10 to the power of 2. And if we are using a centrifuge scaling factor of 100, it means that our general grain size distribution curve should shift to towards the finer side by a factor of 10. And for this, we might go from sand into silt, and we know that this is or potentially has a huge impact on the behavior. Mm-hmm. Therefore, it is generally suggested not to use option 1, which is modifying the grain size distribution, but working with the viscous fluid, basically.
So due to the scaling, we use the same material, and the particles, if you multiply by 100, it's like having gravel, let's say. Instead of sand, you have like gravel. So the pores are much larger, correct? And then you have much higher permeability. So you increase viscosity with the methodology you are presenting, yes, so that you compensate for this scaling issue.
Exactly, yes.
Yeah. Okay, thank you very much, Amin, for this clarification, which I think is useful for someone who is not so much specialized in this kind of modeling. But of course, many people connected here are probably experts. So let's continue. Is there any questions until this here? Any other question? I don't see any raised hands, so we can proceed to the next block.
Yeah, so I will unmute myself again. Yeah, the second block will also be presented by me. So this is on the rheology of the fluid that we have just manufactured. Okay, so now we're getting somewhere. So the first slide is a little bit on the testing protocol that we used in order to quantify the rheological properties of this fluid. There's two things I want to address in this slide. The first one is the hardware configuration. So basically, what kind of equipment are we using to quantify these properties? Secondly, the measurement characteristics. So what kind of measurement are we doing, and how did we define this measurement, or what did we tweak about this measurement? So starting with the first part in terms of the hardware. So we're using a rotational viscometer by a manufacturer called Anton Paar. The specific type I've also highlighted here, but they come in many different versions. And this one uses the Searle principle in order to measure the viscosity. Now, later on in this slide, I will come back to this, so I will park that for a second. The device is shown over here. So we have a concentric cylinder, which will essentially go down into a small measurement cup that contains our fluid. The dimensions of this cylinder are listed over here. Subsequently, it will start to spin, exerting a certain force on the fluid. And then from a small equation, I will come back to this as well, we can then calculate the viscosity. Now, in order to do this properly, you need to make sure that the temperature of this solution is controlled. So for this reason, we use a temperature control unit, and it's actually paired up with a thermo-insulating lid. So that means that we have also no evaporation during our experiment. Now, then if we look a little bit more into the measurement characteristics, I will now show the Searle principle. What we are doing here in order to quantify the properties is a strain sweep analysis. If we then look at this picture over here, is that what we are doing is we are trying to rotate our measuring bob. So that's the pointy part of the figure here, inside our fluid at a predefined speed. So that means that the fluid is experiencing a certain shear rate. Now, what we are doing then is we are measuring the required torque in order to rotate this bob at the required speed. And then, because we know very accurately the dimensions of our measuring bob, we can then also calculate the shear stress. Now, if we have the shear stress and we have the shear rate, we can use this relationship in order to calculate the dynamic viscosity of the fluid. So what we did is we prepared a sample of our fluid, and then subsequently we placed it in the rheometer, and then we did 4 strain sweep analysis. So on every sample, we went 4 times from the lowest shear rate, which is 0.1, all the way up to 1000, which is shown on the right-hand side of this figure. And then what we are getting at each of these shear rates is the back-calculated viscosity value. So then you can see these 4 lines. You can see that at the lower shear rates, they fluctuate a little bit. But if we then take an average, which is what we did for all of our samples, you can see that this fluctuation is basically taken out. And then what you end up with is 2 regions if you look at the measurements. So you end up with a linear viscoelastic region where the viscosity is constant for a certain shear rate domain. And at some point, in this case of the HPMC fluids, we start to see a deviation from this trend. Now, this is a non-Newtonian kind of behavior, and particularly because the viscosity is decreasing, we call this shear thinning. Now, relating back to the story that Amin mentioned at the beginning of the presentation, what we like to do for our experiment is make sure that we couple, let's say, the decay and the generation of water pressures by means of using a viscous fluid. So what this is showing us is that it is very important to be familiar with what kind of shear rates we can expect inside of our experiment in such a way that we can make sure that the viscosity of fluid which we desire is actually obtained at that shear rate. And if you mismatch it, you can end up with a fluid which has a lower viscosity than you actually intended. And then we're only partially compensating for this discrepancy between the dynamic and the diffusive timescale. So if we then look at the rheology of various types of HPMC, because we did not look at one particular type, we actually considered 3 types. So they are listed over here. Let me first say that the prime differentiator between the different types is the nominal viscosity, as I would like to call it. So this is the viscosity that is obtained if you get a solution, so mixed with water, at 2% concentration. And what you can see is that between the different types, this more or less varies by 1 order of magnitude. Now we have a very clear application for these fluids. So in any case, we want to use a fluid that has more or less 50 millipascal seconds viscosity. So this is basically what we try to achieve. So we vary the concentration of each of these types of fluids in such a way that we obtain the right viscosity. Now, we then plot essentially the same chart as I've just shown. I'm just going to introduce one more extra set of axes, which is the viscosity measurement normalized by a reference viscosity. And then our reference viscosity is a viscosity that we obtain more or less in the middle of the linear viscoelastic region. So that is where we have a Newtonian flow behavior. Now, the line that is currently shown is water, which is, let's say, the pore fluid in reality, so in the prototype scale. What we then see is that we get a viscosity that is equal to 1 millipascal second. And if we normalize it, because it's fully Newtonian, we end up with a line that is completely positioned at 1, so unity. Now, if we introduce the first fluid, as a little disclaimer, the concentration of this solution is shown over here in this little box. So right now we're looking at a 2.08% concentration fluid. Of F50, we see that it's mostly following the horizontal line plotted by the water, so the reference. Only at the end, we see a little bit of deviation here, but I would say that this is still a reasonably a good result. If we then continue to increase the viscosity grade of our fluid, what we can see is that there's definitely a lot more shear thinning, and that also the range in which we are seeing the shear thinning is increasing. So if we look at the percentage of decay at the highest shear rate, which is 1000 here, we are seeing that we obtain approximately 15% decrease with respect to the reference viscosity, which should be approximately 50 millipascal second. There's a bit of a trade-off here because we can use a lower concentration. So that means we're using less powder. That means that the density of our fluid is even closer to water. And because we're using less powder, it might be more economically advantageous to use such a kind of fluid. But we need to be wary of the fact that we are observing this shear thinning. Now, if you go to an even higher viscosity grade, we are amplifying these effects. What we can see here is that we lower the concentration to 0.73, but we are seeing that at the highest shear rate, our fluid has decreased approximately 30% in terms of its viscosity. So this is one part of the story. Another part of the story is how can we make these fluids? And well, in that case, we needed a relationship that relates the concentration to the obtained viscosity. Now, I've already highlighted that these fluids exert or exhibit shear thinning. So for this analysis, we looked at a shear rate that lies in the middle of our viscoelastic region. So all of these measurements relate to a shear rate of 10. That's just an important disclaimer. Now, if we look at the results that we have obtained for the 3 different kinds of HPMC, you can see that we get nice point clouds and that they are also different. Let's say the slope of these is increasing. And as I already mentioned, if you use a higher viscosity grade, you need a lower concentration. Now, if we look at what other researchers produced, we were able to find 2 references for the F50 type and 1 reference for the F450. So those are also listed over here. And they propose to use a power law indicated over here at the bottom, which relates the viscosity to the concentration by means of 2 fitting coefficients, so A and B. Now, if you look at the best fitting relationship that we then would get for the results that we have obtained here, also using a power law, you can see that we can find a relationship which actually, which nicely captures the trend in our data. But we should note that it is different from the trends that were proposed by other researchers. Now, this is not necessarily a problem because here we have all of the knowledge in order to calibrate our solutions using this fitting relationship. But let's say for researchers that are new to this area and that need to start essentially from scratch with a fresh batch of HPMC, this could be problematic because none of the relationships that exist currently would probably exactly fit the powder that they are using. So although I will not go into the details in this presentation, what we're currently doing here is trying to come up with a unified formulation that can basically, by means of a single parameter, which is the viscosity at a known concentration, calibrate these curves so that you can completely get the whole curve only by doing a single measurement on one batch of viscous fluid. So Miguel will touch upon this paper later on, but this is something I want to say. So if you're new to this, feel free to reach out to us. We will be more than happy to help you in calibrating a fitting expression based on the type of HPMC that you're using. Well, at least provided that it's listed in this figure here. So with that being said, that brings me to the end of this section as well. I will be more than happy to take any questions from the audience.
Thanks a lot. So next, this is the next opportunity for questions. Somebody has a question? I will start one. I mean, in the previous slide, it's very interesting that when we look at F4M, there is practically no scatter. It's perfect, which is not the case for the other two. What are potential reasons for this perfection, let's say, in one case, and the scatter which seems to be increasing? I think the biggest scatter seems to be in F50. So what do you have any idea what could be the reason?
Yeah, thank you, Jans. It's a very good question. So what I must say is that because this type of powder, we have only tested it in very small amounts. So I was showing in the previous block, like these small test batches of fluid. And what we were doing is we were only testing F4M in those small test batches, because quite quickly after doing the rheological testing, we realized that the shear thinning effect was quite substantial. And for that reason, we would probably not use it in our centrifuge experiments. Because we were very focused, especially with those test batches, on making sure that our measurements were very, very accurate in terms of how much powder are we adding, how much water are we adding. I think that might have helped to produce results that are a little bit more in agreement. On the other hand, I should also say that contrary to, let's say, the other fluids, we did not produce any check batches. So we didn't try to make a batch at the same concentration and see if the measurement was exactly the same. So for this reason, it might also be an artifact that we artificially introduced into our data.
Okay, thank you. And can we imagine, I mean, the curves have the same style, let's say. Can we imagine somehow some kind of normalization of the horizontal axis so that we have, let's say, a dimensional curve? Would something like this be possible?
Yeah, that would be the ideal solution, I would say. So right now, what we are trying to do is to come up with a unifying relationship for each particular type of HPMC, so not taking them all together. But it is on the table to look into possibilities of sort of indeed normalizing the horizontal axis as well, in such a way that we can sort of fit all of them using a single relationship. But so far, unfortunately, we have not managed to succeed. But this would be the ideal solution.
Okay, very nice. Is there any other question from the audience? I don't want to monopolize the questions. Okay, maybe people will, let's say, warm up a bit later. So if I don't see any raised hands, so maybe we proceed to the next block.
All right, sounds good. Yeah, so this is block 4. So this is has to do with the sample preparation. So just a little bit of overview. We have discussed how we are making these fluids, but we want to test them in the centrifuge. So that means that they need to be introduced into the soil. And this block basically highlights the process that we have here at the university in order to make this happen. So this was our initial conceptual design of how we wanted to saturate our samples. So there's 2 main components to this. On the left-hand side, we have a vacuum chamber. So naturally, we can evacuate all of the air in here so that there's no more air. And because we also placed a strong box with dry pluriated sand, here we're also taking out all of the air of our sample. Now, the second part of the system is a storage cell that contains fluid. We need to make sure that the fluid is de-aired. And there's 2 regulators that we have. So we have a physical head difference. So as you can see, the storage cell is positioned slightly higher than our vacuum chamber. And secondly, we have a valve, which also allows us to regulate the pressure between the 2 systems. So if we then look at the total heads that are applicable here, we have a head of our sample here, and then we have a head in the fluid, which is related to the additional component due to the regulator and also the physical height difference. Now, I should say that these, of course, change as we are basically flushing the fluid from the storage cell into the vacuum chamber, but initially the configuration is like this. Now, we did encounter some challenges trying to bring this setup to life, and the first one considers leaks. So over here we have the same overview again, and in red I have highlighted the possible points of air infiltration. So when we first tested this system, as you can also see over here in figure A, you can see that there was all sorts of air bubbles moving through the connecting tubes. Now, naturally, I said that we want to make sure that everything is, let's say, free of air. So the movement of these air bubbles is definitely not beneficial to the quality of our final sample. So we had to address this. Now, the solution is quite trivial, and it basically involves checking all of the connection points and also checking all of the valves. And indeed, we found that some of these connection points were leaking, and also we had 1 or 2 faulty valves in our system. So after replacing those, eventually we ended up with the system that is shown in figure B. And then what you can see is essentially that the fluid is completely free of air. So this is exactly what you want for this kind of system. Now, even after we did this, we still realized that there were still some air bubbles in our fluid. So, well, quickly enough, and after also some brainstorming sessions with the technicians here, we figured that we might have dissolution of gas. So the fluid might still have some dissolved gases in there, and they come out of solution as soon as we start flushing our fluid. Now, this is quite quickly to resolve. First of all, you should take sufficient time to de-air your fluid. So currently we are taking, let's say, 24 hours in order to de-air a complete batch, which is then 30 to 40 liters of fluid, to make sure that all of the air has been evacuated. Now, we did realize that we can speed this process up a little bit. For example, if we agitate the fluid slightly, in our case, we are using a small magnetic stirrer. But also here we should be careful, because if we agitate too much, we're actually mixing in air. And also we can have cavitation of our fluid, which is also not what we want. Then we introduce another phase difference into our system. Now, the third solution is a little bit counterintuitive, but it also proves to be very effective. And that is if we keep the pressure in the vacuum cell, so that's the H sample, slightly higher than the one in the storage cell. So that's just, let's say, the vacuum pressure that is applied above the sample. So I'm not talking about the head and the physical difference here. So if we do this, then we can make sure that we do not have any dissolution of gases as we are flushing it through. However, that also means that we can only accommodate a certain head difference. So that means that the whole process of flushing the fluid is slowed down. So it's a little bit of a trade-off between time and, let's say, making sure that we absolutely do not have any dissolution of gas. Now, the final challenge that we faced was uplift of our sample. So I've highlighted that in these 4 figures. So the first 2 are actually slowing the normal process. So what we are seeing is that the fluid is slowly making it through the sample, and it's starting to saturate the top of our sample here. And then in point C, we see that we have a completely saturated sample. However, at this point, we also realize that the difference between the top of our sample and, let's say, the top of our strongbox had decreased. So at this point, we were able to identify that there was essentially fluid which was lifting our entire sample up inside the strongbox. Now, if we continue to let this play out, eventually what we ended up with was a sample that was completely at the flush with the rim of our strongbox. And that fluid was, instead of sort of building up on the top of our sample, it was going over the sides of our strongbox. So this is obviously not what we wanted. And in the end, we realized that this is very important to make sure that the flow rate is accurately controlled. So it requires some trial and error, but now we have a solution where the sample stays nicely in place and we still achieve the saturated result. So then that is what is shown over here in the last slide. Over here on the left is the setup that we have currently in the basement of our university. And then here on the right, I'm highlighting the process that we use in order to prepare a sample. So as previously said, we start out with a dry pluvriated sample at a pre-specified relative density. Subsequently, we place it inside the vacuum chamber and we connect all of the hoses in order to make sure that we can start flushing the fluid later on. Next, we close up the vacuum cell. We evacuate all of the air and then we open the valve. So then at this point, the fluid will start flowing from our storage cell into our sample container. Now, if we let this run for approximately 24 hours, what we end up with is a nicely saturated sample. It's still sitting at the bottom of our strongbox, which is good. And we have a small layer of viscous fluid on the top. And then the final step is ultimately to take it out of our vacuum chamber. In this case, I've placed it on the side of the setup on the table, but it will be moved obviously from here into the centrifuge room, and then we will connect all of the sensors and use this sample for our experiments. So that also brings me to the end of this part.
Thank you very much. This brings us to questions. Who would like to ask a question? So how bad are these bubbles?
Yeah, that's a good question. How bad are the bubbles? It's well, a little bit difficult to say. Let's say we have not quantified this. But let's say sort of intuitive feeling for us was we want to make sure that we have something that's completely free of bubbles so that the water can sort of, or the viscous fluid can flow through the pores as it would also do normally in, let's say, prototype conditions. So for this reason, we try to focus on really getting rid of all of the air and then not having to worry about this problem.
Okay, I see Alessandra Rosati is raising.
Yeah.
Yes.
Hi, can you hear me?
Yes.
Hi. Sorry. So I'm an ex-PhD student now working for the offshore industry, and I have this question for all of you. Actually, this is something that is in the back of my mind, that I associate the use of a viscous fluid. I was looking at that also in the conceptual design you were showing us. I associate the use of a viscous fluid to experiments involving the use of coarse-grained material like sand, for instance. But what I'm thinking is that the problem of the mismatch between the two scaling laws for time still stands even when we use fine-grained materials like clay, I think, no? But in experiments involving clay, the question is, do we use viscous fluid? And if not, why?
I can jump in. Hi, Alessandra.
Hi, Miguel.
yes, if you use clay, you will still have that generation of excess pore pressures, and you will still have the dissipation of those excess pore pressures. So using a viscous fluid will allow you to compensate for that potential mismatch, as Amin was showing. Even though in clays, because of the permeability, the dissipation might happen slowly, we still use the centrifuge to accelerate the dissipation. That's why when we try to simulate the consolidation of a clay layer, we require less time than it will be required in a full prototype scale. So my answer will be yes, you still will need to use a viscous fluid because you will still have that mismatch between the dynamic process and the dissipation process.
Okay, thank you.
Thank you. Is there another question? I will ask something. Do you have a way to measure the saturation degree?
Yeah, so we are measuring it, although let's say not completely directly, because we wanted to make sure indeed that, let's say, based on the properties of our soil, we would sort of be able to make sure that we have actually transferred sufficient fluid to fill up the entire pore volume.
Mm-hmm.
So the way in which we do this is we essentially weigh the strongbox prior to the saturation process. So because we know the dimensions and we know the properties of our sands, we can calculate a volume of pores. And also after the saturation process, we do the same. So we weigh it again. So the added weight will come from the fluid. We will do our absolute best to measure how much fluid is on top of our soil sample, which of course introduces a slight ambiguity into the result, but we think it's okay. And then based on these two results, we can then calculate whether we have, to a satisfactory degree, filled the complete pore volume. And we can even back check it because we can also look at the amount, or let's say the volume of fluid that has since been missing from the storage cell. So that's this one here. And then if we do this, let's say double checking in these two ways, we come to the conclusion that the degree of saturation is very, very high. So based on the measurements that I took, we are talking about 98% to 100%. But as I told you, there's a little bit of play there due to measurement errors. But I think it's good enough.
Okay, thank you. Is there any other question?
If I may, I can add some experience of measurement of degree of saturation, and that is the use of small-scale time domain reflectometers. These are basically electromagnetic devices that they measure the electrical permittivity of the material. And the value of electrical permittivity of water has, the value is much higher than what the air has, or the material, the soil type of material have. So so this value actually is quite sensitive to the amount of water. And by knowing, and so it would be a direct measurement of the volumetric water content of the material. And knowing the porosity of the material, or a good estimate of the porosity or void ratio of the material, we can actually have a good estimate of degree of saturation. However, I must say that the technology at the moment for TDRs, these time domain reflectometers, is not yet mature to have a good sampling volume for very small scale centrifuge models. So that's something to be developed, but it's for larger scale samples, like the one that Tristan is showing on this slide. this technology or this type of sensors may be used as well. Of course, it should be checked for the permittivity of the, or should be calibrated for the permittivity of the viscous fluid that is used instead of water.
Mm-hmm. Thank you, Amin.
You're welcome.
Okay, so if we don't have any other question at this time, we proceed to the next block.
Let's do it. Yeah, so this is the, well, before the conclusions, this is the final block. And this is where we start moving into the centrifuge. So this is a brief slide just to highlight what we are using for our experiments. In a nutshell, what we are doing is we are generating a dynamic event. In this case, it is the blow of a hammer on top of a pile. And due to the energy transferred between the hammer and the pile propagates into the soil dynamically. And because the soil is saturated, we are then interested in the saturated soil response. Now, in order to measure this, we are using the Strongbox as is shown over here on the right. We are using a number of pressure transducers. In this case, we are using 9 pressure transducers. These are installed at 3 different levels, so 3 depths. And also they are positioned at 3 different radii with respect to the centroid of the pile. Now, as you can see, the pressure transducers that we are using are located outside of our Strongbox. This was essentially a practical decision in order to make sure that, let's say, the volume inside the Strongbox that is not occupied by soil is as small as possible. And as you can see, the whole system with all of the connections, etc., is quite bulky. So in this way, it is better to make sure that we do not affect our measurements too much. Now, then, of course, the question is, how do you measure something inside the Strongbox if your sensor is located outside the Strongbox? And that is where these capillary tubes come in. So we have very rigid capillary tubes made from stainless steel that are protruding inside our sample. And then at the end of each one of them, we have a pour stone. So that's also indicated. So that allows, let's say, the pressure regime that is located at this point in our Strongbox to be transferred through the capillary tube down to our pressure transducer. And obviously, for this to work properly, we need to make sure that this entire system is completely saturated. So that's also why you can see this little point sticking out here. So what we do prior to starting our test is we essentially attach a syringe over here on this end, and then we apply a little bit of vacuum pressure. So we pull on the syringe, and then we are pulling through fluid from inside our Strongbox through the whole system in order to evacuate all of the air that is inside of this system to make sure that it's completely saturated when we are conducting our experiment. So then the first step of the actual experiment is to pre-install the pile. So I have also included a little video over here. This is playing at 10 times the speed. And the pre-installation of the pile actually is conducted both at 1G and then subsequently at NG. So this is only showing the installation of the pile for NG. So what we are doing is we're placing the pile right above the soil sample. We are releasing it, and then essentially we are allowing it to settle completely under its own weight. And then after it has come to a stop under 1G conditions, we continue at NG. And then what we are getting is, let's say, these 2 settlement bumps that are shown in by the dashed lines over here. The subsequent part is conducting, let's say, these dynamic events. So hitting the pile numerous times in order to drive it down to the desired depth. And in our case, that was always approximately 3 pile diameters into the soil, which is more or less the embedment level for very large offshore piles. Now, we then look at the different results that we have obtained because we did this for 3 different types of saturation media. So we used water, F50 and F4M. And we basically wanted to make the comparison between, first of all, the generated pore pressures. If I speak generally, what you can see is that the profiles, the installation profiles, all look more or less similar. So what we are seeing is that we are, as we are conducting our blows, we are getting this stepwise installation profile. but it slowly flattens off. And that has to do, amongst other things, with the fact that if the pile is penetrating further into the soil, there's more resistance acting on it. So for the same blow energy, the penetration would be reduced. So then if we go to the actual measurements of the pore water pressure sensors, this is what we will obtain. Now, there's a lot of information on this slide, so I will try to provide a little bit of background first. Over here on the right-hand side, we have a schematic illustration of our strongbox. This is an axisymmetric illustration, actually. We have our pile, and then we have 3 of our sensors. So these are labeled shallow, middle, and deep. And I should also say that the position of the pile also reflects the position at which we conducted our measurements. So this was the situation when we were doing our measurements. So what we can see is that our shallow and middle pore water pressure sensor have been surpassed by the tip of the pile, and the deep one is yet to be surpassed. So then if we go into what is shown over here, as I've told you, we have a shallow, a middle, and a deep pore water pressure sensor. And then we looked at our results for the 3 different types of saturation media. So we have water on the left-hand side, we have F50 in the middle, and we have F4M on the right. And the parameter that we are plotting here is the liquefaction ratio. So the definition of this is the dynamic pore pressure. So that is our actual measurement from the sensor. From this, we subtract the hydrostatic back pressure. So this is the hydrostatic back pressure located at each level, at the level of each of these sensors. So it's different for each sensor. And also we are dividing by the effective stress. So I should also say that this is the effective stress assuming hydrostatic conditions, again, at the respective depths for each of these sensors. Now, if we look at the results, and I first want to make the comparison between water and viscous fluid, so I'm sort of summating the results of F4M and F50, what we can clearly see, and it ties in very closely with the thing that was highlighted by Amin at the beginning of this presentation, is that if we are using water, we are measuring a very small response. If you just look in terms of magnitude of the signal, we are talking about, let's say, 5 to 10 times difference in some cases. And subsequently, what we can also see, apart from the magnitude difference, is that the decay is really, really quick. What we can see from the water measurements is that we lose all of our pore water pressures after approximately 0.3 seconds. And this is to do with the fact that the permeability of our soil, in this case, with using water as a pore fluid, is 50 times higher than in the prototype. So whatever we are generating, we're essentially dissipating straight away. Now, if we start to introduce a viscous fluid, the results change quite dramatically. And we can immediately observe that the process that we are dealing with is not fully drained, definitely. It can be potentially fully undrained, really at the moment of hitting the pile, which is a very, very short time duration. And then probably we get a partially drained response of our soil. So then if we look at the results for the shallow and the middle pore water pressure transducer, is what we can see is we get essentially the generation of excess pore water pressures in the area where the sensors are located. So that has been surpassed by the tip of the pile. Now, if we then look at the deep sensor, so that's a point which still needs to be surpassed by the pile, what we are seeing is a negative RU. So that means that the measured pore pressure is lower than the hydrostatic back pressure. So essentially, we're getting more or less a dilative response of the soil, which is causing a drop in our pore pressures and therefore an increase in the effective stresses that are located at the tip of the pile here. So this is a very interesting observation. So based on where we are looking, so which sensor and where it is located with respect to the pile, we see that we are changing, let's say, the sign of our RU. Now, if we make a closer comparison then between F50 and F4M, so F4M is one of the fluids which we know has a lot of shear thinning effects, and F50 is more or less fully Newtonian. What we can see is that especially after these, like, let's say, sharp peaks, the decaying rate in the F4M is a lot quicker than in the F50. So you can see that, for example, over here, if you compare it with the results of the F50 one, and even more clearly over here, if you compare this peak over here with the one over here for FOM. And so this brings us a little bit to the point where we are trying to see that, let's say, improperly accounting for the effects of shear thinning inside let's say the design of your experimental study could in fact have an impact on the results that you are obtaining. Now, I must also say that this is still work in progress. So we are trying to quantify this better and also get a better understanding in terms of the theoretical backbone of this. But it does seem that shear thinning effects are something that should be considered, and that especially with these dynamic installation experiments, the use of let's say, pore fluid that is viscous in order to compensate this discrepancy is highly recommended, because it does affect the effective stress state and therefore the entire behavior of soil that is occurring at the moment where we are driving these piles. So in that sense, I think this is also an important observation to make. And that actually was the last slide of this section as well. So I would be more than happy to answer any questions related to this too.
Thank you very much. These are for these very interesting experiments. So what questions do we have? Jorge was the fastest.
It's very quick.
Hi, everyone. Jorge Mendoza from University of Southampton. I have a question regarding the instrumentation on this system. So I can see pore pressures are normally very localized, and the saturation of the fluid plays a critical role on how we measure that. So my question is, how did you test this setup before putting into the centrifuge? Was there any type of prototype that you tried on a laboratory bench with maybe some volume controllers to see if the pressure of the viscous fluid could be transferred into a line that is saturated with the air water?
Yes, thank you for the question, Jorge. Very good question as well. So the way that we tested the functionality of this system was indeed, as you are saying, although we did not test on a dry bench, we essentially tested in the centrifuge. And what we did is we filled our strongbox with water, but also with viscous solution. So we did not use any soil. So we filled the entire box, and then what we did is we did, let's say, a sweep through our centrifuge, starting at a low G level and then going up to G level 50, 60 times gravity, and then measuring the response of our pore water pressure transducers. And then based on the analysis of this, what we were seeing is that the trend that you would expect based on the increase in G level was very well captured by our pore pressure transducers, up to the point where we are approaching the intrinsic measurement frequency, because these transducers can only log up to a frequency of 1 kilohertz. So if the dynamic event is a lot quicker than this, arguably you should use different kinds of sensors. But for the application that we tested here, we feel that they are giving us nice results, considering, let's say, how difficult it is to implement these sensors, and also how they perform during testing.
Okay, thank you very much.
Very welcome.
So these capillary tubes, I'm wondering, as you spin up and the soil settles, but these are stiff. What happens? How does this perform?
Yeah, so that's also another good question. This is the reason why we wanted to make them very stiff. So we don't want them to flex, let's say, with the soil. Also because they might start to resonate, because during the dynamic event, there's all sorts of stress waves passing through. This is something that we do not want. So I agree that, yeah, this is a little bit of a question mark, though what we are trying to do, also by means of preparing these samples, is to make sure that the soil is completely densified around our capillaries. So these are quite small. I think the diameter of this is only 3 millimeters. And because we are also, after raining in the sand, vibrating the sample for a short period of time, it is our feeling that the soil will have compacted nicely around the capillary tubes. And then also, if you look at our measurements, because we have also had some experiments where we did not properly, let's say, compact the soil around the sensors, what you can see is that if you are increasing the G level in the centrifuge, because the density of the soil surrounding the capillary tube is lower, you sort of get a small collapse of the soil around the capillary tube.
Mm.
And in turn, this will give actually a measurement that it can be observed by the pressure transducers. And what we are seeing now is that we are getting a very smooth curve, which is exactly like the curve of the centrifuge acceleration. That doesn't show any weird peaks that could sort of hint towards a collapse of the soil matrix surrounding the capillary tubes.
Mm-hmm. Okay, thanks. Other questions? Sumin. Please unmute yourself.
Yeah. Can you hear me?
Yes.
Yes.
Thank you again for the presentation. And I have a quick question. So what are the viscosities of each solution?
Yeah, that's a good point. I did not highlight this in the presentation. So water, as mentioned previously, it doesn't have viscosity, so the viscosity is 1. And for F50 and FRM, the target viscosity was 50 millipascal second, so 50 times the viscosity of water.
And what was the G level that you tested?
50 G.
How do you expect the results to differ when you using like solutions with a different viscosities? Like using like 30 times fluid or like 60 times fluid or something like that.
Yeah, so I think that's probably also partially captured in here. So as we hypothesized, it is likely that the viscosity of our F4M fluid, because of the shear thinning effect, is lower than 50. Like we know it's 50 at the low shear rate, but because the shear rate that we are generating with the dynamic installation of the pile is actually quite high, we anticipate that the viscosity here is lower than anticipated. And then what you can see, assuming that the results for F50 are actually correct, is that there's differences between the two curves. And yeah, to address the point of why we are using specifically F50, that is essentially because that is what the centrifuge scaling law tells us to do. There might be some applications in which you could, for example, use higher viscosity fluids, like larger than what is dictated by the scaling law. But this is, in our case, outside of the scope of the experiments that we are conducting.
Thank you.
If I can add, in those cases where you go higher than the scaling factor, what the purpose is there is to really keep those excess forward pressures there. So you're forcing your system to dissipate very, very slowly. But there are some groups that tend to do twice the N factor they're using in their experiment just to keep those excess forward pressures there and induce as close as possible an endrained response.
Mm-hmm. I'm wondering in slide 29. So first of all, this is prototype time or model time? It's model time, right?
Yes, model time.
So, and every plateau that we see is between the various hits.
Correct, yeah.
So you hit and then you wait, how much is this? Like 500 seconds?
Well, this is a good point. Like it's in that case, this figure is not entirely representative. the device that we are using is a single blow actuator. So that means that it can only conduct a single blow. And then in order to reset the actuator, which that needs to happen manually, we need to stop the centrifuge and reinitiate again.
Ah, okay. So
So
you need to spin down.
exactly, yeah.
Ah, okay.
So let's say the reliable point of this graph is, let's say, the increment in normalized embedment that we are measuring, because this is all the time for 50G. And then what we are seeing priorly and after is essentially elastic compression and relaxation of the soil due to the change in G level.
Okay, but in reality, each blow would be much closer to the previous one, right?
Yes, correct.
So we could have development of excess pore water pressures, and if there is no time for dissipation, maybe the RU could go significantly higher because of accumulation. Is this correct or not?
Yeah, but I will add that in Tristan's work, his purpose is to understand what happens after one single blow.
Okay, okay.
So not to capture that whole process of installation, that will come after.
We're working on it.
But at this stage, is to clearly understand what happens in a single blow under everything very well controlled.
Mm-hmm. And why is water between F50 and F4M?
Yeah, so this is something we're still investigating here. But we are not quite sure yet. I should also be honest about this. What could happen, because let's say water is our benchmark. So essentially, what my initial expectation was is that the two the two viscous fluids would end up below water, because we are having this undrained response, and actually it's restraining the movement of the pile a little bit. So the displacements would be smaller. Now, what you can already see at the beginning here, and that is probably one of the things that we need to investigate a bit further, is that the initial settlement of these piles is different. So that is something that is not accounted for, let's say, in this figure. So you can see that the F4M is pre-embedded up to a level of, let's say, 1.8, whilst let's say the F50, which is in orange, is pre-embedded up to a level of 1.4. So they're not exactly equalitarian. So we are working on this right now. I'm writing a script to do it. We're going to normalize the stress state in order to make sure that the stresses surrounding the pile are equivalent. And then we will replot the same figure. I have a feeling that it will change the appearance of this. And if not, we have something more to investigate the coming months.
Very nice. Good. So, is there any other question? I don't see any raised hands. Kill one co.
Yeah, can you hear me?
Yes.
Yeah, thank you for the nice presentation. I have a short question from your presentation. So do you happen to compare the pore pressure responses with numerical or large scale tests, so you could come to the conclusion of which the preparation procedures are good method to represent the field case?
That's a very nice question. Thank you. So in this particular case, and that mostly has to do with the nature of the installation method that we are testing, we don't have a prototype benchmark. So unfortunately, currently, we cannot compare against prototype scale experiments. However, we are working also together with our industrial partner on developing a code, a numerical code. I think it's an NPM model, to sort of see whether we can, at least on the computer, and then for the small scale that we are modeling over here, replicate the results that we are obtaining from the centrifuge. Now, we are part of a research group here at the university, and there's also other installation methods that we are investigating, of which there are actually good benchmark tests, possibly also from prototype scale. And there, indeed, it is our aim to quantify, let's say, how well the match is between our centrifuge experiments, scaled to prototype scale, and the prototype benchmark. But unfortunately, it will not be at least for the moment, for this particular installation method.
Okay, thank you.
Thank you.
Good. Thank you very much. I think it's time to wrap it up
Yep.
with the conclusions.
Very good. So I will be relatively quick for the sake of time. So after all that we have shown, we can agree that the preparation of viscous fluids have reached some level of maturity between our community. We have shown that among the different options of HPMC viscous fluids, there is indeed a difference, and that difference is connected to the fact that there is a shear thinning process under high shear rates, and therefore the selection of a viscous fluid needs to be mindful of that fact. When we design our experiment, we probably know already what type or what is the range of shear rates we will be expecting, and based on that, we probably can make an educated guess on what will be the effect of the shear thinning factor of our viscous fluid. As Tristan has shown, it is not just preparing the viscous fluid that is important, it's also the saturation and accounting for all those little details, those little bubbles that can get into the sample that might interfere with the proper saturation of our model, those potential leaks that might be a source of error to the amount of volume we are expecting to flush into the model, and all those potential issues also at the level of the sensors we use. So this is one of the experiments we are developing with this type of viscous fluid, but it's important to mention that the protocol we are developing for the preparation and saturation of these samples will be used for other applications. So those of you who are interested to read more about this, I would like to point you to this paper that Tristan will be presenting at the upcoming European Conference on Physical Modeling in Geotechnics that is going to be held in the first week of October here in Delft. And also to invite you to participate. This is one of the events organized by the TC, and the proceedings from this conference will be open access at the moment of the conference in the ISSMG conference review platform. So yeah, happy to answer any questions that these conclusions may lead, but more than we would like to thank also the support and the funding that is provided by our industrial partner IQIP, and to all the technical support we received through all this process, in particular to Roland Klassen, who unfortunately couldn't be today with us because he recently became a father and there are more important things in life. So yeah, thank you so much for your attention and happy to answer any questions.
Thank you very much. Let's see if there is any final question. I would like to thank you, to thank the speakers for delivering an excellent webinar, which is exactly at the heart of the idea about these webinars. Because, you know, usually we have, we present usually, especially in conferences, we present a success story. It is a success story, but going through the various problems, the challenges, and how these were solved, this is the best way to learn. And I think this webinar today did exactly this very well. So for this reason, I would like us all to thank the speakers for really delivering this webinar exactly within the concept of the whole idea. So thanks a lot. It's a webinar, so we can only clap with virtual hands, but I think this is the time to do it. So thanks a lot. And I would also like to thank all the participants for being here with us and also for participating and for making this really interactive. I think it worked really well. I enjoyed it a lot. There was a very interesting discussion, a lot of questions, and I'm really looking forward to repeating this with other speakers and proceeding with this initiative further. Thank you very much.
Thank you, Amin. Thank you all.
Yeah, thank you, everyone.
Thank you.
Thank you. Bye.
Bye-bye.
Bye-bye.